Okay, well, I suppose I'll get going. So no announcements this week, I guess. Nothing interesting. Oh, I made the quiz due tonight instead of Saturday. I'm sure people noticed because Blackboard tells you when things are due, to my knowledge. So yeah, I just made it due today in case people had quick questions. Although immediately after this class, I have another class next door. So if you want to ask me questions and it's not quick, you'll have to wait until I'm done that class at, hold on, 7:30. But I'm happy to answer questions after that if you have any. So that quiz was on recursion. So we only had one class last week, so I tried to figure out a topic that fits into just one class along with a worksheet. So I thought, let's talk about recursion, which are mathematically and in terms of programming just functions that refer to themselves. They call themselves in terms of programming. And there are lots and lots and lots of algorithms and mathematical formulas and stuff like that that are recursive. I gave an example. I defined factorial recursively, which is a bad way to do it. Don't do that. But a classic one is the Fibonacci numbers. They're defined recursively. So it's f of n is f of n minus 1 plus f of n minus 2, where f of, I guess you could call it 0 is 1 and f of 1 is 1. That's a pretty classical recursive definition. So they're all over the place. The Fibonacci sequence is pretty important in a lot of things because it gets us something called the golden rule, which is a special constant that appears all over the place in like spirals and in nature and stuff like that. So it's kind of interesting. But the point is there are lots of really interesting recursive formulas and algorithms. And I'm going to talk about more of them as we go on. So that's why it's important to just introduce you to the concept, especially in the topic we're about to cover. There's a couple of things that are defined recursively, and just having that understanding of what recursion is helps, because there are a lot of algorithms that if you do them recursively, you implement them in like 4 lines if you understand them. So getting into the next topic, so I'm going to say this for the video too, if people are watching. So we're going to talk about graph theory, which I've mentioned in the past. There was a section about proofs and all that stuff, like formal proofs. Nobody liked it. Nobody liked doing the exercise. Well, actually, it's funny. I've talked to students who I took it out. They're like, oh, but I love that. And I'm like, well, where were you when I was planning this? So it turns out some people liked it, but most people didn't. And it wasn't really applicable to anything you're going to do, right? I didn't have an answer to why do you want to learn this. So I tried to think of something to replace it with, which is graph theory, which there are lots of answers to why you would care about it. But I have to mention, I have never taught graph theory before, in the sense of giving a formal lecture. Like, I've explained it to people and talked about it a lot, but I've never given a formal lecture on graph theory before. So this is new territory for me. I made the notes over the weekend, so maybe they're not great. Maybe I'll fumble. Maybe things here I'll go too fast. I'll go too slow. Maybe things will be really simple and we'll be done in a day, and I'll be really embarrassed because then I'll be like, I don't know what we're doing on Wednesday. Maybe we'll be going over time and I'll be like, oh no, I have to cut some stuff. I don't know. So we'll just kind of see how it goes. So definitely let me know if things are, not making sense or whatever. I'll go over it as much as I can. So when we're talking about graph theory, we don't mean what people think of as a graph, right? We're not talking about parabolas or something like that, right? This is not what graph theory is. Graph theory is actually a discrete math topic. So this is something that's called continuous, right? Because you can draw your pen without ever lifting, whereas discrete is like single points like that, right? So this is a discrete topic, meaning it is sort of finite. It's not some weird curvy thing like this. And they crop up all over the place. I'm going to give you several examples of where graphs appear naturally and why we would care about them and the algorithms we're going to talk about. But we'll start with the definition of a graph. And this definition is very mathy. Unfortunately, If you want to implement graphs or trees, something we'll talk about in programming, understanding this definition is fundamental. Like this definition is literally how you would implement it in an object-oriented programming language. So this definition is kind of important. You might use a dictionary to help with it, but so a graph G, it consists of two sets. One called the set of vertices. So that's a word that we're going to be using a lot, vertices. I might accidentally say node, because when we're talking about computing, we would say node instead of vertex when we're talking about trees. So these, I might use them interchangeably. I'm going to try to stick to vertex and vertices because that's the math word. Which we call V. So this is usually just a set of labels, right? It's either going to be letters or numbers or strings, whatever, right? It's just basically labels that we're going to use for points. Then we have a set of edges, which we call E, for edge. These edges are unordered pairs of vertices. So that means this set is kind of weird. It's a set of sets where you're going to have just unordered pairs of vertices, and that's going to indicate an edge. So I'm going to write down some examples, and then I'm going to show you why we call this a graph, because right now this seems kind of weird. We're just talking about two different sets here, but I mean, the names kind of indicate that there's something more graphical going on here. So, for examples, we're going to say, suppose V is the following vertices, A, B, C, and D. Right? So it's just a set of labels, right? They're just letters. And we're going to take a set of edges. And so this is what I mean. It's kind of weird, right? It's a set of sets. I'm going to make sure since I've never talked about this specific set of notes before, I'm going to be looking at this a lot, which is kind of embarrassing. Just to make sure I have the same ones. So this is what it looks like. So we've got here, these are all sets inside of a bigger set. So now when we're talking about a graph, why do we call it that? Well, generally speaking, we will visualize this thing. So each of these vertices we'll draw as circles, right? And we'll fill them in with, this is A, B, C, and D. And now these are edges because they indicate a connection between these vertices, right? This is saying A and B are connected. This is saying A and C are connected. And this is saying A and D are connected. Right, so we've got these connections between these vertices. Right, and so you can kind of see now, it's not graph in what you're used to seeing, but you can kind of see there's sort of a pictorial representation of this data set, right? It sort of represents just connections. So let's just go through another couple examples. Suppose these examples are distinct and specific ways that I want to talk about. So I'm gonna call this like example A. Wait, that's bad. I shouldn't circle it and call it A because I'm already doing that. You know what? Yeah, numbers.
Numbers in a math class?
Yeah, we'll use numbers to indicate. So this is graph number 1, right? So we've got our vertices now. We're just doing A, B, C, right? And our set of edges is going to be AA, AB, AC, and C, comma C. Now, there's something interesting going on here, because we've said in sets we remove duplicates. So this is a weird little exception that we're making right now for demonstration purposes. Generally speaking, you would call this a multi-set. But we're going to not turn our attention to these types of graphs because they're really bad. But I want to show you that this is still technically a graph. So where can I put this? I'll just put it right here. So this is graph number 2. So we've got our vertices A, B, and C. And this is just saying, hey, there are some ways that they're connected. What this is saying is A is connected to A. So what that essentially means is you're going to go out from A and then back to A. You got this kind of loop going on. And this is saying, hey, A is connected to B, A is connected to C, and C is connected to itself. So we've got that loop going on there, right? Okay, so that's another example of a graph. It satisfies our properties. Again, ignoring the fact that we're saying these are unordered pairs. This would technically be a multi-set, but they do crop up pretty often in graphs when we're talking about specific applications, so it's unfortunately worth mentioning. And one more, called graph number 3. B is going to be A, B, C, D, and the set of edges is going to be just A, B, C, D. Okay, so what does this look like? Well, again, we have 4 vertices, so we just draw them. A, B, C, D. And now we draw our connections. A is connected to B, C is connected to D. And that's it, right? This is also a graph. But you can kind of look at these and notice that there are certain differences between these graphs, right? Like this one here looks pretty rigid, right? It's just, you've got a vertex and lines coming out of it to other distinct vertices. Here, we have these loops, right? We've got A is connected to A, C is connected to C. Here, we essentially have 2, sort of distinct chunks, right? But this is still one graph, right? They're different pieces, but this is still one graph. But because these are sort of distinct situations, we do actually have names for them. So there are names to distinguish these 3 cases. So the first one, I'm going to say it this way, it rules out this one. And I'm using that word specifically because in some sense, this and this are what we would call degenerate cases, right? They come up in applications, like we do care about them, but a lot of things that we take for granted don't work for these 2 types, right? We're interested in nice looking ones, generally speaking, which is sort of counter to how math is when we're normally like, no, we're interested in the ugly looking ones. We want the bad ones. In this case, actually, we want the good ones. So a graph is called simple if it contains no loops. That's literally the definition. A graph is called simple if it contains no loops. Okay, great. So this graph is simple. These 2 are not. Now, to take care of that one, we have the notion of whether or not a graph is connected. So this is kind of a mouthful, but it's sort of an intuitive thing because graphs are pictorial, right? You can draw them. if I'm going to call something connected, I think you would agree with me, that is not, right? Because if I wanted to go from A to D, I can't, right? So it's sort of, there's two chunks here, right? So a graph is called connected if given any point in the graph, there is a path from it to every other point. In a graph, let's change that word, given any vertex in a graph, there is a path from that vertex to any other. Right, so we take a look at this. If I pick A, I can't get to D. So this is not connected, right? Because I would need to pick any vertex and be able to get to any other. Whereas we look at these, if I pick B and I want to get to C, there we go, right? Here, if I want to go from D to C, there we go, right? So connectedness really is sort of, everything is sort of connected, right? It's a pretty natural word. It matches your intuition, which that's kind of one of the nice things about graph theory is a lot of the, and discrete math in general, actually. This is, I want to lean more into it because discrete math is very accessible. It's very sensible. Everything kind of has natural analogs to what you would intuitively think. So that's kind of nice. Unlike a lot of calculus and algebra and stuff like that, which can seem obtuse, this usually isn't. So in this section, and kind of just in general, we are going to focus on simple connected graphs, unless indicated otherwise, which in this notes I don't think I do. So from here on, when we say graph, we mean simple and connected. So we're ruling out those degenerate cases because a lot of the techniques and algorithms we're going to talk about don't work for those. Yep. Just like that. So this is something I'm actually about to mention, though, and this is kind of important. There is technically a definition related to something like this that I'm not going to get into, but there is something called graph isomorphism. I just want to mention it really quickly. So an important property of graphs is there's no real one way to draw them. As long as you have the exact same edges in the exact same connections and the same vertices, the graphs are the same. Is so long as we don't remove or add edges and vertices, we can draw a graph however we want. So this is, the word is called isomorphism, which if you get really into math is a word you just hear like nonstop, isomorphism. So the point is, taking a look at this one, so this no longer matches this, by the way. We can move stuff around freely here, right? So instead, so we've got this crisscross here. We could actually remove that, I think, by doing, so we're going to swap that there and maybe we can't actually. But this is still, it's a differently drawn graph, so that's still fine. So where A and B are connected, I wrote D twice. Hold on, where was I going to put B? You know what? Sure, let's put it here. Why not? So A and B are connected. And then we have A and D are connected. B and C are connected. And C and D are connected. So we have a different looking graph, right? It's sort of rotated, but these are the same, right? They represent the same idea, right? Essentially, if you were to pick a node and try to go to another node, you could still take the same paths to get there, right? You could go from A to B by going directly, or you could go like that, and it's the same thing here, right? You'll still visit the same exact places. So it's essentially just, you can draw it however you want as long as you have the right number of edges and vertices, right? You're not removing or adding things or missing things. So that's kind of convenient. Okay, so one thing when we're talking about graphs is we kind of notice here, well, actually, this is a bad example because they're all degree 2. But there's some number of edges sticking out of every vertex, right? So here there's 2 edges, 2, 2, and 2, right, coming out of it. And so that's actually something that ends up being important. We sort of capture that. Another important property of graphs is degree. Which again, it's funny that we use some words that scare students in math, but this one is actually not that bad. Degree is just the number of edges that stick out of a vertex. So degree of a vertex. Again, we're using the word vertex all the time. Remember, it's just one of these. It's just a point or node or whatever you want to call it. It's just one of those. Is the number of edges that stick out, or lack of a better word, or are connected from that vertex. So let me just give another example of a graph. So we've got that bigger. A, B, C, and D. So this is what our graph looks like. We could talk about the degree of every single one of these vertices. And the notation we would usually use is just DG, degree. You don't have to use that notation. You could just say the degree is whatever. But the degree of A, we just have to look. How many edges stick out of it? 2. The degree of B, how many edges stick out? 2. The degree of C, how many edges stick out? 3. And the degree of D is 1. There's only 1 edge that sticks out of it, right? Yep.
I've done something a little similar to this before, and one of the rules that you can use to tell whether or not something is fully connected, like if all parts of a maze are accessible,
Yeah.
to any isolated vertex's neighbor has to have a degree higher than 2.
That is true. Yep. So there's actually so many theorems about graph theory, and that's actually one that I thought about talking about. I might put on the assignment. Is you can use graph theory to solve mazes, like at a very easy glance. And one of the search techniques related to graphs, breadth first search, will always solve a maze very quickly for you. So Good point. So anyway, we have this concept of degree. We also have, you can talk about the degree of a graph, which is going back to what you were saying. It's just the biggest degree of all of the vertices, right? So the degree of the whole graph, so we're calling this graph G, is 3. The biggest degree in the graph. And like sets and that sort of thing, it's very similar. Uppercase letters generally represent a graph. Lowercase letters would represent vertices, sort of like with sets. Uppercase was the set, lowercase was the elements of the set. We just have that sort of distinction. Although, again, like I said, I'm using letters just for, convenient notation. You can put whatever you want on these vertices. You could put numbers, you could put cities, that sort of stuff. Yeah.
So this is just like a pictorial representation of a polynomial?
So you can connect it to a polynomial, but it's not really that related. So you could do something like the coefficients of a polynomial somehow connect to nodes on a graph, and you can use it to do some techniques with polynomials. But there is something interesting about a graph, and it's how computers essentially do arithmetic and no order of operations. You can take a mathematical expression like a times b plus c minus d plus e, and you can actually break it down into a graph, and it will preserve the order of operations in an interesting way. I don't remember the name of the notation though. It's not human readable for what it's worth. Like it's I think it's like Belgian notation or something like that. I don't remember. But it breaks it down. It would be like minus times plus a b c. Like it's totally unreadable, but it's machine readable, and that's the important thing, right? So that's another application of graphs, is that it helps it know order. You can easily do order of operations when you have brackets and different operations and stuff like that. So this is why I love this topic, because like I can just, if someone's like, what about this? I can be like, oh yeah, here's a reason where graphs are relevant in computing, right? They're literally everywhere. A program is a graph, right? If you think about it, you've got something at the top, which is like the initialization or the main routine or whatever like that, and then it branches down into a bunch of subroutines and subcalls and stuff like that, right? So graphs are everywhere. Okay, so one thing I want to mention is so we've already sort of mentioned some, right? I defined the idea of a simple graph, the idea of a connected graph. There are so many subtypes and classifications for graphs that if I could honestly probably spend like a month talking about it, of each different one, and here's the application of this specific type of graph, right? We're not going to do that. I'm just going to keep it as simple as we can. What I do want to mention, there are tons of types and classifications of graphs. So we'll try to talk about only the important ones, or important to us. But that means if you happen to know of a specific type of graph and you're like, hey, what about this? Then I'll be like, hey, on Wednesday we can talk about it, right? Again, there's so many different things here. So I mostly want to stick to ones that we care about in computing, though, because there are lots that are outside of that, like Hamiltonian graphs. I don't think really have a whole lot of application in computing, but you can talk about Hamiltonian graphs and Hamiltonian cycles. They're useful in math, but not really in computing. But an example that is sort of natural, and you can think of lots of reasons why we would care, but a lot of the stuff that we want to talk about need a lot of modifications for these types of graphs, but it's the idea of a directed graph. So a graph, we'll call it G, is called directed if, well, you have a set of vertices and a set of edges E, which are now ordered pairs. So in the previous definition, we said unordered pairs, right? It didn't matter if it was A comma B or B comma A. Now we're saying, no, actually we care, right? This matters. So technically, the previous graphs were called undirected. But we'll only specify directed if we need to. So that means if I say a graph, you can assume it's not this type. It's going to be an undirected one. And it kind of makes sense because if we start caring about connections, then some of the things we've talked about don't necessarily work anymore, right? So here's an example. So this is saying you can only go along that direction, right? And technically you can have both directions, right? There's nothing wrong with that. You can have go in either direction here, but both directions is not guaranteed. So an example of what does it mean to be connected now? Well, you can't get to D if you start anywhere here, right? But this is still, intuitively, we look at it and we're like, yeah, but we have like lines connecting all of them. So with a directed graph, that's not quite enough. The definition is still the same, but we have something called weakly connected and strongly connected. This is weakly connected because if we got rid of the arrows, we got a connected graph, right? It makes sense. But strongly connected would be you can actually get to any node along a directed path. So the point is, directed graphs get a lot more complicated, right? But let's try to capture this graph in terms of our definition. And what does this graph actually look like in terms of sets? Well, in this case, we've got our graph G here, vertices. Well, these are the same as before. So now it's our edges that look different. So let's take a look here. So we've got an edge that goes from A to C, but now we're going to use round brackets to say this is an ordered pair. Remember, this means ordered pair like a coordinate, right? An XY coordinate. The order matters here. A comma C is not the same thing as C comma A when we use these round brackets. So we can go from A to C. We can go from C to B. We can go from B to A. But we can go from A to B. And we can go from D to C. Right, so now we actually have this quote-unquote duplicate, but since it's an ordered pair, it's not actually a duplicate anymore, right? This is B comma A, this is A comma B. So another example. Let's do this one. A, B, C, D. I'm going to number these again. Okay, so we've got some edges here. And I have to copy them down again because I don't have the example memorized. It's embarrassing. A comma B, A comma C, B comma C, C comma B, C comma D, B comma B. Okay, how do we draw this? Same as always, right? We've got our vertices, A, B, C, and D. And I might end up with some crisscrossing here because I'm drawing it differently than in my notes. So this is saying go from A to B, but make sure we pay attention to the direction. Right, so that arrow indicates we go from A to B. A can go to C. B can go to C. C can go to B. So we just take the same path and draw an arrow. C can go to D. And D can go to B. So this is another one of those examples, right, where we can get stuck on this thing, right? If we go from A to B, we can't go anywhere else anymore, right? We're stuck there now. Oh, sorry, yeah, no, this is, aha, yes, we can go both ways. So maybe it isn't one of those graphs. So we can go from A to B to C to D, B to C to A to B to D, C to D to B to A, and so on. So we get this one, actually, we can get from anywhere to anywhere else. So this, again, I'm not drawing a distinction here because it's not that important. This is weakly connected, strongly connected. Because sometimes it is important to know the distinction of, you know, is my graph contiguous, right? Like, is it all connected in the intuitive sense of like it's one big chunk, or is it connected in the sense of going from A to B, right? Yep.
You can't get to A from A.
Hold on. Because now my example is ruined if we don't have that. C comma A. Okay, there we go. Now we should be good. Because we can get to A from C, and we can get from C to anywhere, and we're good. Okay. But good catch. This is what I mean. I'm going to fumble on this. I've never done these examples before. Some of these I'm inventing on the spot, too, so that's why it's kind of like that. But the point is, with directed graphs, you may not be able to reach certain places from other places. So you can kind of actually think of a natural application of directed graphs. Think the road network of a city. Not every road is bidirectional, right? Some of them are one way. So in theory, a directed graph would be useful when planning your city to make sure, hey, we have a bunch of one-way roads. Is it really, really tediously awful to turn around or get from this point to that point? Now, we've all been in cities where you think about it, you're like, they sure didn't do that. Like downtown Edmonton is a nightmare sometimes. But that would be an application of it, right? You're really trying to plan your city to be, you know, easy to get around. You would draw this out and make sure that it's strongly connected, ideally, and then you would look at the connections to be like, how many vertices do I have to visit to get from A to D, right? Like in this case, to get from A to D kind of sucks, right? I have to go all the way across my city, essentially, right? Well, I guess I could go down this way, but you know, maybe it would be nice to have a direct path because that's a popular destination or something. So that's one situation I thought of where it's like, yeah, I've seen graphs in that situation. Another example of a graph type is pretty natural as well, and it's the idea of a weighted graph. So a weighted graph, as the name kind of implies, is one where we just assign weights either to the edges or to the vertices. Where we assign weights to either edges or vertices. And you could do both. You could do either. So situations where you would want to assign it to vertices, maybe the importance of a node. So you're like, okay, I've got this collection of places. I want to make sure I visit the most important first. Like I have a priority system of visiting these locations. And weighted edges would be, time, right? How long does it take to get from each node to another node, right? So weighted edges typically refer to time or distance. And weighted vertices refer to, weights essentially, so priorities. So you think, okay, I have a travel plan. I want to visit these 10 cities and I've ranked them in order of importance, right? So let's plan a route that makes sure I hit all of these cities in a certain order. And if I run out of time, then I skip my lowest priority cities, right? So that's where we would have weighted vertices instead. So an example of a quick weighted graph. Is something like this. A, B, and C. So the way we'd indicate weights on edges is we just simply put them on the edges. Like this, right? So if we think of this as representing, say, time or distance, it turns out going from A to C and then from C to B is the faster way to get to B from A, right? So if this represents time, or distance, going A to C to B, so this would be 2 and 3, is faster than just the direct route, which is 10, right? So again, graphs are sort of abstract concepts, right? So this is not necessarily to scale, especially when we're talking about, well, again, abstract concept. The visualization here is mostly to help you sort of understand what's going on. If you were building this as a data structure in a computer, you don't necessarily have the visualization, but it can still solve the same problems, right? It still represents the same thing. So you might still ask yourself, what's the fastest way to get from A to B? But now you don't have this picture, right? You just have the weights and knowing that they're connected. So in that case, you would say, okay, well, going this way is faster, right? And if you were to draw it to scale, then, this would be, actually, this is hard to draw to scale because of it's a triangle, right? So it's going to get really squished in really weird ways. This is going to actually, I think this might even be an impossible triangle technically with those lengths because of Pythagorean theorem. So anyway, the point is you might run into situations that don't even make sense in terms of a picture with weighted graphs, but they're still data structures that you would represent, right? These still are things that you would do. And it's because time might not just be explicitly distance, right? It might be like, well, there's a bunch of construction along this way, right? So now this takes way longer, even though it's closer, right? So lots of stuff like that. But that's kind of the use of it, right? If you think of like trying to build a transportation network or a delivery network, you might want to keep track of all these distances, right? So that your system can automatically say the fastest way to get from this store to that store is to go this way, right now. So think of like maps, Google Maps or something, right? It'll dynamically adjust to be like, hey, here's what you do. And really the way a GPS works is just really, really advanced graph theory. Like actually that what it does is it sort of assigns these weights to various nodes and vertices and just sort of calculates optimal distances based on that. In terms of our definition, we can think of natural ways to sort of capture these weights. So like just think this graph right here is our vertices are the same, A, B, C. But our edges, what can we do? Well, if we knew that our edges always look this way, what you could actually do in terms of data structure is we could say, well, I have an ordered pair of an unordered pair, A, comma, C. And in that ordered pair, I also have the weight, right? So this is saying this is the connection, that's the weight, right? And so then it would be C comma B, that's 3, and A comma B, which is 10. So this looks uncomfortable, but as you get used to programming more and more, this type of stuff is really common, right? Like you'll have like a dictionary of sets which contain tuples, right? Like, and that's like that looks really ugly to write down, but I mean, maybe that's what you need for your application. This right here is, well, a graph is best represented as a dictionary, and those values would be tuples, which the first one is a set and the second one is an integer, right? So that's like a very complicated sounding data structure, but it captures what we're looking for. Okay, so now that we've sort of talked about some, basic concepts of graphs, this is something that I didn't know where to put in, and maybe I should have put it as the very first thing, but it's actually some history on where graph theory actually came from. It was developed in the late 1700s from a problem that was proposed to a mathematician, Leonhard Euler, and it's called the Seven Bridges of, hold on, I have it written down, Königsberg. So in this situation, I have to try to draw this picture. Please don't judge my artistic skills. But he has this city, which is sort of got these rivers in it. And we've got these islands, right? So this is a city. You've got houses here, and we've got some bridges on it. So we have a bridge here. We have a bridge here. We have a bridge here, and a bridge here. There's a bridge here. One here, and one here. This is historically accurate. This is what the city looked like. Well, not that. That looks terrible. But I mean, this configuration of the city with these exact bridges and these exact land masses did actually exist, and probably mostly still exists. I don't like maybe some of the bridges have been torn down, but this is still on that same landmass. So the question that was proposed to him was, can you start anywhere in this city and essentially cross all of these bridges exactly once and sort of just do a tour of the city, right? So like, can you start, say, on this landmass and cross every bridge once? Oh, well, now we're stuck, right? Okay, well, what if we started here? We're stuck again, right? So that was the question, right? Can you solve this problem? Like, how could I possibly do this? I don't know. It might have been someone, I don't know the exact history, but someone might have just been like, hey, I would like to do this tour. How could I do it? And he was like, okay, well, maybe we do this. And so you probably look at this, and if you like puzzles, you're probably trying to solve it. I'll spoil it for you. You can't. It's impossible. So he kind of noticed that. He was working through this, and he was like, man, I can't seem to get it. Right? Something is preventing me from being able to tackle this problem. And he noticed a couple things. One of them is that the only thing that matters here is the connections between the land masses, and that's it, right? Nothing else matters. Just, from here, I can get to this landmass twice, right? There's two ways to get there. So what he did was he said, okay, I want to make sure I draw the same picture I have in my notes. He sort of represented it pictorially. He said, okay, I have two ways to get to this landmass, and I have two ways to get to this landmass from here, one like that, and like that. So he got a graph, right? This is literally a graph. He actually wrote down something like this in his notes in the margins, right? Like he actually started doing some abstraction like this. And then he was like, okay, well, if we're looking at this problem and I start anywhere, if I go to a destination, in order to leave, I have to go across another bridge, right? A separate one, which means every place I go to has to have an even number of edges, right? If I'm to leave that, right? Because if I go here, I have to leave it, right? If I want to get back to the same destination. If you don't, then it turns out the starting place and the ending place don't have to have an even number because you leave it once and enter it once, right? So like if I started here and said, I don't care where I end as long as I do everything, then I only have to leave here once, and I only have to end here by going in once. But the point is, most of these have to have an even number of edges, right? Because if I enter it, I have to leave it. So he noticed in order to leave somewhere, or I should say, when entering a location, you must leave, requiring an even number of bridges. And that kind of makes sense, but then we take a look at this. In the modern language we just started talking about, the degree here of this node, 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. And 1, 2, 3. So in fact, none of these have an even number of nodes or edges, and that's why we get stuck every time we try it, no matter where we start, no matter which path we take, right? Because it's literally impossible because of the degrees. If instead we modified this problem, let's do this. It's possible now, right? Start here, go around like this, boom, we're done, right? Like here, I'll draw the path. So we go around like this, and we end there. Right? We've only used every edge once, but we have crossed every single edge. So he also noticed, he was like, hey, in that situation, I have exactly two odds, right? This one and this one. I have to start in the odd and end in the odd. Right? So this actually led to a definition which ends up coming up for a lot of problems in just logic and science. And because he was the one who discovered it, we named it after him. This is called an Eulerian trail. Is a path through a graph that uses each edge once and only once and only once and technically you can start and stop in separate places. There's something called an Eulerian cycle, or circuit, where you start and end in the same exact spot. But specifically here, we're talking about trails, so you could start and end. There's no condition on where you start and end. So a graph has one. If and only if there are exactly 0 or 2 degree or vertices with odd degree. Are exactly 0 or 2 vertices of odd degree. So that means our original formulation of this problem, where we had paths like that, doesn't satisfy that. So we can't, this does not exist. In fact, he actually only proved one direction of this originally, and sort of postulated that the other one was true. He said, well, if it satisfies that property, 0 or 2, then I can find the path, right? And he would find it. The other direction that was later proved in, I don't know, the 1800s or something like that. It was posthumous. They found it in his memoirs. He proved it before he died, but never published it, that the other direction was true. That if it has one, then it actually satisfies this property. But anyway, this is kind of just, so this is two things. One, it's kind of fun to see historical math where it's like, you look at this and you're like, hey, we just worked out this problem in like, not very much time, and there was a guy who dedicated like a good chunk of his life to solving this problem. But we have the gift of hindsight. We have a definition for this stuff, and we have ways of talking about it that are more sophisticated than he had at the time. So we can laugh at his primitive mathematics and solve it easily ourselves. But it is also interesting that like it's accessible, right? Because this again was some deep research, and there's actually a lot of applications of this specific concept, but it stemmed from some very specific like puzzle, essentially, right? He developed an entire branch of mathematics from an unusual puzzle that someone presented to him. So I just think that's kind of fun. But you can imagine situations where trying to find these paths is useful, because, well, it's essentially going along a path without ever backtracking, right? So just think, you're going on a road trip across Canada and you're trying to hit X number of cities, but you're like, it would be boring to drive down Highway 2 again, right? So you want to hit a different road every time. So you would look for an Eulerian trail through that, right? And you wouldn't call it that, but you would, when you're planning it, that's what you're doing, right? You're looking through all of it and sort of planning it so that you don't traverse the same edge more than once. And it's kind of funny that you might end up in situations where you're like, wait, I actually can't do this road trip, right? Because it doesn't satisfy this property. I would say most of the time, though, you would have exactly 2 connections, because it's something like a map like that. You're going across Canada to like these destinations. So you're going to go like this. So they all have degree 2. So like it makes sense, but it is still kind of interesting to think about. Or at least I think so. I'm, nerdy like that. Okay, so again, we're just going to talk about more applications here. I'm just kind of rapid fire, and essentially, like whatever's most interesting, you should tell me, because that's the one that I would emphasize more, or talk about more, or make a homework problem, because I haven't made the homework yet. So, another one is graph coloring. So this is essentially just an algorithm that assigns colors to the vertices of a graph, where no connected vertices share the same color. So we can color a graph such that no 2 connected vertices share a color. That's a pretty simple algorithm, actually, but it's interesting because computationally, problems related to it are exceptionally difficult. I think some of them are even NP hard, which if you know what that means, then you know that they're bad. So an example would be, I have a graph with this many edges and this many vertices. How many ways can I color that graph? Right? That's a hugely complicated problem at that. But the algorithm is easy to describe. So you've got your graph. The first thing you're going to do is just pick a color of your choice, right? Start with a color. A color. And index it as color 1 or 0 if you want to think in terms of arrays and indexing that way. Pick a vertex. Color it with this color. Right? Okay. Now we essentially pick a vertex, right? Pick a connected vertex. And a new color. And index it as 2. And color. Right? Because we started with a vertex, colored it in, and then we're going to pick a neighboring one and color it a different color, right? Because they can't be the same color. So on and so forth. So essentially what we do is we pick a connected vertex after this. So I suppose I could say ... right? Just sort of keep repeating this in a way. Color the vertex you just found with the color that has lowest index unused by neighbors. So, okay, this sounds like a mouthful. Let's actually, color a graph using this algorithm. You can kind of see it's, this one isn't, you might be able to implement it recursively, but I don't think that's natural. Because you are shrinking the problem essentially, right? You color a vertex and then, you color the rest of the graph. But in order to color that graph, you need to remember everything that precedes it. So it doesn't really shrink the problem. You still need to know the scope of the whole problem. So let's go like this. And I have it just like this. A, B, C, D. So, okay, let's look at the algorithm. It says, start with a color. I got green. So green is indexed as number 1. Pick a vertex. Who cares? B. Color it in. All right. Pick another vertex and another color that's connected to this. Color it in. Now, we have to grab another connected vertex and ask ourselves, okay, pick the lowest color here, and if there isn't one, I need to make a new one. Right, so I look at this and I say, well, can I color it green? No, because this one's green. Can I color it red? No, because this one's red. So, okay, I need a new color then. And now we move along. There's still one more left. We get to this one and we say, okay, Can I color it green? No, because this is green. Can I color it red? Yes, actually, because it's not connected to any red ones. So we color that red. So this algorithm will actually produce a minimal coloring. So it will use the smallest number of colors possible. I think if you pick, I don't remember if it depends on the vertex that you pick. It might. So you might actually have to run this algorithm on every vertex to make sure that you have the minimal color set. But this is something that you've probably actually seen in action more times than you would think. So, I don't know what a map of the U.S. looks like. I don't know, something like this. You got Texas and like that. And you've got all these sort of states, right? It's a map. How do you color this in so that none of the adjacent states have the same color? Right? Well, you can actually make a graph out of this, right? So these are all connected. Let's say that's not connected. That one's connected. Right? So you've got this sort of messy web like this, but you perform this algorithm, right? You say, okay, well, start with green, color it in, pick one, color it red, pick one, okay, well, I can color this green, pick this one, I can color it red, this one, I can color green. This is a bad example because, like, it kind of worked out. This one here, I have to color it blue. And so on and so forth, right? So this is actually what the algorithm that they use to color maps so that they look nice, right? And implementing the algorithm in terms of programming is kind of a challenge. Especially, so actually doing it just arbitrarily, just say, all right, just pick a coloring, I don't really care. It's pretty trivial, right? Because you just implement the algorithm directly. But when you say, okay, I want the smallest number of colors possible, right? Like maybe if I started here, I would have got a smaller number of colors used. That's when it starts to get really complicated. Okay, so any questions so far? Because the next one I want to talk about is kind of I would say the meat of graph theory that I wanted to talk about. So I want to make sure that I cover anything that anyone has. Because this is the one we're actually going to talk about algorithms and stuff. Nope. Okey doke. So in terms of programming, there is a specific type of graph that is exceptionally important. It is a data structure that is very, very useful for specific applications, and that's called a tree. So one of the most important, or I would say it is probably the most important graphs. Important graph subtypes for computing is called, technically, it's called a rooted tree because there's a graph. The graph theory and computing don't entirely agree here. So we have this extra word to make sure that we are talking the same language, but we're just going to sort of ignore that for now. So a tree is a graph satisfying the following properties. So the first one is that we have a very specific vertex that we're essentially calling important, and we're calling it the root. There is one vertex designated the root. And from that root, all other vertices stem, right? They all can trace back to that root. From this root, all other edges and vertices originate. Maybe not directly, but like there's a path going from there, right? From the root to anything. So this is essentially the top. Which, funny choice of language. The roots of a tree are generally not at the top of a tree, but anyway, that's the language we chose. There's one other condition on a tree, and it's that if there are n vertices, then there are exactly n minus 1 edges. So actually this condition right here, there's actually like 10 different ways you can phrase this. This one, when we're talking about computing, is important. We need this condition. But this one, there's a bunch of equivalent conditions to be called a tree. I think this is the most accessible one because it's literally just draw it and then count stuff, right? But you could talk about it in terms of being connected and, well, I don't have to write that because we're assuming all graphs are connected from this point. But it's connected and no cycles or something like that. I don't remember specifically, but there are lots of conditions here. Lots of equivalent definitions. So let's actually just visualize what one of these looks like. So the most basic example here would be something like this. I don't know if I have enough space. I'm gonna give this. So I have a, it doesn't matter what I call the letters. Like that. So tree-like structure, right? This is called the root, right? Because that's sort of, everything comes from here, right? Everything can sort of stem from that top node. But let's see if these conditions are satisfied, right? We're calling that the root. Everything stems from there. There are 1, 2, 3, 4, 5, 6, 7, 8 vertices. 1, 2, 3, 4, 5, 6, 7 edges, right? So when you have this property here, you get something that's sort of structured like this. And like any graph, you could draw it in however you want, but generally speaking, this is how people draw it, right? Because you have sort of this descendant structure here, right? You've got something at the very top and then stuff sort of cascades down from there. So there's actually another piece of terminology here. If a vertex has degree 1 in a tree, we call it a leaf. Again, I think this is very funny that we call this the root at the top of a tree, but then we call these bottommost ones leaves. I don't know. Like, what's the top of a tree, though? Like, we don't have a name for that in language. Yeah, I mean, we could call it the top, I guess, but that's not what we did. So these nodes right here that sort of are at the bottom of a tree are called leaves. Okay, so we also have some additional terminology here to sort of be on the same page about. We have the idea of parents and children, and when you're looking at this picture, like they're what you would expect, right? So like, just intuitively, this node has no children. The parent of this is B, right? This has a parent A, it has children C and F, right? So that definition is intuitive, but let's just make sure we write it down. So the parent, actually writing it down is actually going to make it worse probably, of a vertex on a tree is the vertex connected to that vertex. Let's give this a name, vertex V, towards the root. So that's just basically a very wordy way of saying what I just described, right? Why is this the parent? Because if we're looking here, there's a vertex connected to it. This is the one that's on the way to the root. Looking here, there are actually 3 vertices connected to this, and this, but only one of them is on the path to the root, right? So this would be the parent because it takes us towards the root. A child of a vertex V is, well, it's defined in terms of parents, right? This is a child of V because it has V as a parent. So a child of a vertex V, let's give this a name too. A child X of a vertex V has V as its parent. So again, these are, I'm mostly just writing these down so that we have a frame of reference, but they're the sensible definitions here, right? If you just sort of think about this picture of a tree, parent means what you think it does, child means what you think it does, leaf makes sense. The only word that doesn't make sense is root. It's at the top of the structure. Okay, well, there's like 4 minutes left, and I want to give a couple more examples of trees, and then I want to talk about sort of search methods for trees and binary trees, and if I have the capacity to do so, I want to briefly talk about something called a binary search tree, which is a way of encapsulating binary search, and you can do binary sort using binary search trees, which I think is kind of cool. But that's a lot of like computing science theory that is maybe not worth talking about. But from a mathematical perspective, I can talk about the trees themselves, right? I can talk about the tree structures and what they do and why we would care. But the idea of a binary search tree is actually kind of a lot in terms of how to implement one, so I won't do that too much. But I hope at least so far you're kind of seeing that there's like a lot of algorithms associated with these, and especially on Wednesday I'm going to talk about these search algorithms, which are kind of fun to implement in programming. So I will probably make you do that on a much later project. At this point, if you had no programming knowledge, you're not ready for that. But by the end of the term, you should be. We'll see. It's one of those things where I'm going to assign it, and then if everyone's like, Travis, we have no idea how to do this, I'll be like, good to know. I won't do it again.